Hello everyone, thanks for joining the session by Kaggle Days Meetup Delhi NCR. It's today our 33rd meetup and we really are very much honored to host Mani Sarkar at our meetup or online meetup. Definitely we could not have hosted him in an offline one, given the time zone differences we have and the things that we need to take care of. So today we have Mani who would be discussing and would help us to understand the limitations of statistical measurements, why and why not, and a lot of other things on statistical measurements, and would help us to clear certain things which might be like why this topic sounds interesting. It's like whenever you go to interviews, might be there are cases that you face this kind of like questions, or maybe you have certain doubts around this. So maybe this session of today is useful, and I'm very much hopeful that Mani would help us do that. Over to you, Mani. Mani is a Kaggle 3x expert, and I would leave the stage to Mani to introduce him because his profile is too diversified. And yes, it's interesting to have such personalities on the stage to help us understand, help us like gain knowledge. Over to you, Mani.
Cool. Thank you, Ion. So thank you, everyone. We've been waiting for this for quite some time, nearly a couple of weeks. So as you can see from the title, we'll be discussing the limitations of statistical measurements. And, we will see what topics we will cover. And as Ion has so nicely said, that it hopefully will help you understand in your personal journeys as well. So a little bit about myself. So I'm a senior software data machine learning engineer, and I've been doing this for over 18 years, almost 20 years now. I'm also involved with a lot of online communities, and as you can see from various buzzwords here, I've had a lot of involvements, all the way starting from software engineering and to now ML and data science, and also sometimes diving deep into things like statistics, which isn't what I started off with, but I'm picking on those topics as well as I go along. So I won't go into the details of my profile. And Ion was right, it's quite broad and diversified, but there's a link here that can tell you more about my profile. Besides, you'll also get the slides, so you'll get to go deeper into it. We have more interesting topics to talk about, like the topic of this presentation. So we won't spend too much time on my profile. So we have a small agenda to cover. And so, we can start off, but with the things we will cover and, how we'll finish. But before that, I want to let you know that these are the topics of the agenda. We have some sort of introduction of how I started off with this journey and, the thinking that I came across with, and also an explanation of how I thought about these topics and the notebook that I created from it. Now, not everything that I thought about in the notebook is in the notebook. I've also had additional questions that I later on thought about that I didn't put in the notebook, and also some other ideas and insights that came about, which I wanted to also share with you, which is not in the notebook, but it's going to be part of this presentation. And towards the end, we will have some more questions, because we're going to be wearing some sort of a critical thinking hat while we are going through this topic. And so we need to keep asking questions, and you'll see what those questions are, and they'll keep growing in generality. We'll finally close the session with some summary and closing and sharing of resources. And then there's a Q&A session, which has been allocated after this presentation is finished. Also, with every presentation that I do, I have some sort of an appendix section that I add to my slides, because there are a lot of resources that are in my slides that don't fit in as part of the presentation. So I add them to the appendix section. One more thing is I wanted to share is that that these slides are now available online, and you can actually go to them. So this is the bit.ly link to go to the slides, and you could also use your phone to scan the QR code, and that'll also lead you to this link. And then on the link, you will see like a PDF file, which you should download, I recommend, because if you browse through that in the GitHub repository, you won't be able to click on the links. But if you download the PDF file and then you open up in a browser or in a PDF viewer, you should be able to click on the links just like you would click in a normal PDF link. So I'm going to just wait for like half a minute or so for you to get familiar with this link and get download. And in case we miss out, I mean, I have already shared the link with Ion, and I think I see that he's already shared the bit.ly link with the rest of you. I'm assuming this is good enough for now. So I'm going to switch to our presentation, and that takes us to the section where I want to thank Ion and his team, because without him and his team organizing this, and Ion has been very instrumental in getting us to this point, and obviously you, the audience, because without you, this session isn't complete, right? So the both of you are definitely worthy of thanks from me, because this completes the session. I have a small disclaimer that I make with every presentation that I do, and in this specific one, it's no new deal. So I want to bring to your notice that your mileage may vary for this specific topic or topics related to this as compared to where I come from. So please bear that in mind whilst we are going through this presentation. And also that there might be untested ideas or things that might be inaccurate while we are discussing this, because we're only discussing these topics here. Remember, these are sharings from my learnings over the past years and sharings of ideas and experiences that I've had, and they need not necessarily all be perfect and pristine. They're also gathered from various different sources and from different experiences. Moreover, we'll be inquiring about things and not claiming anything. So that way we are not going to be putting us in a position where we are going to be correct or wrong, right? It's always best to be in a neutral position so we don't take a side or a position. And we'll be very playful with the ideas. And remember, at the end of it, we want to take away some ideas also to think further after this presentation. It's not like we do all the thinking at this presentation and that's it. Like, you want to think about this further, and hopefully this presentation is going to help stimulate those kinds of activities. I have a small citation. I've used images from different sources, and I want to thank the owners and the creators of those images. And so I have this standard slide that I always have. So let's actually start with how did I go about with this topic? How did I come about thinking about this topic, come up with a notebook, and then eventually coming up with this presentation? So it so happened that around 2020, you can see from the date on the tweet on the slide, and the other dates mentioned on the article section of the slide, that around 2020, I came across, and I think some of you might know this master, Kaggle master, Carlo, and he has been quite instrumental as well in my journey when I have been on Kaggle, trying to learn and participate in competitions. But so we have these conversations now and then on social media, where at this instance he was sharing the books he has been reading, and then I spotted it and I started a conversation about those books. And then it so happened that one thing led to the other, and a conversation came about around statistical methods and statistics, and how there are shortcomings in it. And you can already see one of the titles of his book that talk about statistical consequences of fat tails. And then after some time, I came across these other articles that you can see on the right-hand side, a couple of them about the trinity of errors that the author speaks about in two different articles. And now, just to assure you, we are not going to cover any of these topics. They're quite advanced and outside my depths. But we will do much simpler discussions and have conversations on much simpler aspects of this topic. So, taking this further, I want to mention that yes, our discussions are going to be simple. The presentation is going to be on simple topics, and also I am going to try to keep this whole the whole discussion simpler by looking at it from a simpler perspective. And this is also what I did when I started writing the notebook. I picked up a simple topic, I mean, it could have been a simpler topic then, but I was thinking of a couple of topics, and one of them stuck. Even then, I think it was a simple topic I started off with. And so that led to the creation of the notebook. So, basically I downloaded all my ideas and thoughts that I had about that topic in a notebook, and I just started expounding on them. And so with that came this notebook, which I've already shared as part of the abstract, which Ion so kindly did when he put together the abstract for me. And you might be having, some of you might already be having the link to the notebook way before this presentation, or maybe as a result of the registering to this presentation. But if you still don't have it, this is a great chance to go and click on that link, or go to this link, and you should be able to do that in the slides. In case you're not able to get to the link, not to worry. At the end of this presentation, there'll be enough time to open up the notebook. But I'm going to wait a second here so you can open up the notebook. We will be picking up bits and pieces of the notebook as we go along. And if you want to browse through them whilst the presentation is going on, I mean, you can freely do that. So let's go into this topic. Like, what did I write in the notebook? What was I thinking about? What were the ideas that were coming to my mind? And this is the first idea that came to my mind. So I picked it up and I started writing about it. And this is not unknown to anybody, especially in the space of data science and machine learning. Correlation coefficient is a widely used term, and you can see from the Wikipedia definition, it helps us measure the correlation between two variables, right? And of all the searchings I've done, I came across this formula, and maybe there are other formulas or formulae to come up with the correlation coefficient, but this one was the first one I came across, and I so decided to share this with the slides. But if you also are interested in computing your correlation coefficient on your own, which you actually don't need to do because there are libraries that are already doing that for us, but if you still want to do that, then there are a couple of links shared at the bottom where it expounds over the formula and also how to write it from scratch in Python. So let's go further into this topic. So what are we actually talking about? So when I was looking at correlation coefficient, this is what occurred to me. I take two distributions, I pass it to this function as a parameter, and it returns to me a single value. So just a couple of thoughts that came to me in my mind was, hey, I'm passing it two distributions, and these distributions can be of various sizes, large or small, but I'm only getting back a single value. And one of the things that occurred to me, this looks like a one-way data compression function, right? And I'll expound on both of these, what I mean by that, as we go along. So it's not like I'm just making comments and not explaining them. But this is what came to my mind, and is that enough information that we are getting back from this function? So firstly, what are the issues with a single value? Like, what are issues with single values that represent a large number of values, right? One of the points is, and this has nothing to do only with specifically with correlation coefficient, but single values in general are they can be terse, they can be too compact and maybe less insightful. There may be a loss of information in the process. And let's say hypothetically, if you have multiple pairs of distributions that you're computing correlation coefficient from, what is the chance that two or more of those pairs may have nearly the same correlation coefficient when those distributions are actually disparate? They're like, there isn't much of a commonality between them. What is the chance of that happening? I mean, I haven't tested this to the hilt, but I'm thinking in theory there is that chance as well, right? Especially because if you have just one number telling you something about hundreds or thousands or millions of numbers and comparing two such sets of numbers, right? So there are a couple of other points that came to my mind, and these need not necessarily be very valid, but they still were points I wanted to throw in. One is this some sort of a black box function? And the second is, can we trace back from that single value back to the distribution? Like, is there some sort of a history maintained of how the end value came about? And I will expound in another example on what I mean by this history of steps, right? So just let's keep this in mind for a second, even though it may not hold much ground at the moment, but when I show you some other examples, maybe it might hold some ground there. So the other question came to my mind is, now, of course, we have these limitations, and I've come across them, and it's a single value. How do I throw some more light on this end result, right? How do I make this end result single value more meaningful? And this is a general question with anything, not just the correlation coefficient. If we have an end result and we don't have enough insight about it, how do we throw more light on it? So that's when I started thinking about this thing, and I came up across these two methods. And I'll throw some light on how these methods are related to existing methods. So these are two experimental in nature methods. One of them is called running correlation coefficient and moving window coefficient, and you'll find both of these in the notebook, and they're expounded in detail, but I'm going to still go over it with you now. And so the running correlation coefficient and the moving correlation coefficient are similar to something called simple moving average. So I think this is something many of us who are familiar with in the data science world, or even in the finance world, are familiar with this simple moving average concept. Basically, you just compute an average at every point till the end, to the last value in the distribution, and you get a running simple moving average of the distribution. So I applied the same thing to the correlation coefficient, but I took it to 2 levels or 3 levels higher. So if you can see from the graph, you have something that says left to right and something says right to left. So what I did is I computed the correlation coefficient for up to every point in the distribution, from the first point till the last point, going from the left of the distribution to the right. And then I also reversed that direction, and I did that from right to left. And then I did something further. I did a difference between those two values, and I also did an average between those two values. And you can see the interesting results that have showed up here. In 3 cases, they're converging to almost the correlation coefficient that is returned by correlation cof function. And in the third case, it's converging to 0, which makes sense, because if you take the difference, it's going to be the difference between those two values, which is going to be close to 0. And in this case, you can see it being close to 0. But you can see that the distribution starts off a bit jagged, and then it smoothens towards the end. So that means there's more information, more nature hidden in the distribution that maybe we are not seeing. So that's one method of throwing light and finding out more about what we've been given. And the other one is moving window coefficient, which is again similar to the simple moving average, except in this case, I'm using something called the windowing or segmented method. What I mean by that, a window is like looking at a small segment of the distribution and running from left to right, but only looking at small segment of distribution at a time. And when we then compute the correlation coefficient from those small segments of windows across, you can see that the correlation coefficient is actually jumping anywhere from positively correlated to negatively correlated and across the board, right? So most of the time it looks like it's positively correlated, but there are instances where it's also negatively correlated, right? So it's something to look and understand. So that's kind of what I started doing. And so moving forward, if we now see, you might ask me, why all these perspectives, right? So if you see, by checking this from in this manner, from like if you see these methods that I've used, we are actually checking the distribution in the forward direction and in the backward direction, right? Unlike just taking the single value that we've been given by the function and not looking at how the distributions are sitting together. We are also using something like a magnifying glass method to actually approach to actually look closer to smaller segments of the distribution and see how do those small sections of the distribution work and act. And I also try to play around with the sorting of the distribution values, and that kind of isn't clear yet what it's going to end up looking like, but it needs some more work. But that's also another angle to look at it, right? So I would actually recommend, I'm not going to go through every section of the notebook because this presentation isn't about that, but there's a lot of commentaries and a lot of examples and a lot of other things in the notebook. And I've expounded on both of these further and given comments. You'll see comments like this, for example. And I've only taken snippets of these comments from the notebook, but in each of them I'm actually showing, after I've expounded it in terms of a plot or a graph or a table, I'm actually explaining the table what do I see there? I see, okay, I'm seeing both left and right, and I'm also seeing positive and negative, and I'm also seeing below 0 and above 0. So this information is hidden away from that one single value information, right? So that's something I've been expounding in the notebook. But I also have a final comment where we actually see all the negatively correlated and positively correlated values in a form of percentiles. And this is a very useful way to also look at a distribution in a more compact form. And then I've put some more comments on it. Again, I'm happy to receive feedback on this. If anybody thinks that there's something missing here or incorrect or something can be improved, I'm happy to take that on and apply it. So moving on, can we say after doing these things that we've done so far in the notebook and now in these slides, are we complete? Have we resolved the limitations, right? So what would you say? I mean, I'm going to say that we could do more, and in fact we need to do more. What we need to do is we need to ask more questions, and what we need to do is extract more qualitative and quantitative information from the correlation coefficients about the distributions. This is what we need to do, because that's kind of what's the missing information that will help us answer some of the discrepancies that might be there between any two pairs of distributions, where the correlation coefficients either are very far and wide apart from each other, or they are very close to each other, given we know the nature of the distributions, right? So we need something to give us more concrete information. And so what are the questions we might want to ask? So that's where I thought about some additional questions that I want to ask to this correlation coefficient information or function, or to the concept. So what are the additional questions? So we know there are positively correlated, negatively correlated, and not correlated distributions, right? But then we also have seen from the graphs that actually in any distribution, there are parts of distribution that are positively correlated, parts of it that are negatively correlated, and sometimes we have small parts of it and sometimes not, that have no correlation. And it's important in the form of questions to ask, how often are these that are positively correlated, and if they are positively correlated, for how long do they stay positively correlated, right? And then also draw some descriptive statistics out of those small segments where they are positively correlated for each of those segments, and capture them, right? So it could be in the form of percentiles, histograms, min, max, we have to figure that out, and capture all of these answers and refer to them in the form of notations. In this case, I've done PC1, PC2, PC3, positively correlated 1. I mean, for a lack of a better name, this is what I'm using now. But obviously, we can always use better names later on. Now, the same questions we ask for negatively correlated segments, right? How often are they negatively correlated? And how long do they stay negatively correlated? And do we have some descriptive statistics for those segments that are negatively correlated, right? This is useful information to know and to have. Now, not to forget, there are also segments, and sometimes this is negligible or absent in distributions, but we don't know. But we still need to ask how often they are not correlated, and when they are not correlated, how long are they not correlated, right? I'm skipping the descriptive statistics part of this because it's not clear yet if I want to gather the descriptive statistics part of it. But if some of you think that, hey, if you've gathered descriptive statistics for the others, why not for this? And it's useful as well. We could do that, because if there's no correlation, then the descriptive statistics may not be that useful. That's my current thinking, but I'm happy to change that thinking if there are examples provided where we actually think that might be useful information. So now the question arises that these additional qualities or quantities or qualities in the quantitative form that we have now gathered from the correlation coefficient information between two distributions, can they help us compare pairs of distributions correlation coefficients, right? And I think we can use that, right? And what would those comparisons look like? Can they look like something like this, right? We say distribution A versus B. In this case, I've used words like normal, random, and Pareto, but they could be anything. And these are just examples. Don't take them to face value. I mean, take them like as an example. Don't take them literally. And if you look at it, you can now see that if we have the qualitative information about these correlation coefficients between the distributions in a quantitative form, we can compare those easily. And even if you have situations where the correlation coefficients are very close to each other, like I've tried to show in this example, but all the other properties and other traits about that differ, and they differ widely or narrowly, we can use that as an argument to say, hey, they may look similar, but they are not, because you see, internally they differ quite a bit. The internal structure is different. And we know this from the all the statistics and all the qualities and quantitative qualities that we've gathered from all the questions that we've asked. So that's one way of looking at it. So now, can we say we can write a better version of the correlation coefficient function? Maybe. Can we not write something like better core cof, and we pass it to distributions? And this is just a very skeleton, experimental idea. We pass it to distributions, and it gives us the normal correlation coefficient that our correlation coefficient functions would give. In addition to that, it also gives us all the quantitative, qualitative information, the quantitative form that we can use for comparing, measuring, etc. analysis. So that's kind of where I was heading towards, which I haven't expounded in the notebook, but hopefully with some discussion, with some experimentation, there'll be another version of the notebook or an update to this current notebook that will that may have this in place. So that was my initial of the various ideas I was thinking about at that time. That was the initial idea I thought about, and I started writing about it. And then when I finished with it, I had more ideas, but it didn't put it in the notebook. But then came this opportunity to give this presentation, and so I took this opportunity to slide these in here. And so this actually fits in quite well with the other pending idea, which I didn't even expound in the notebook, right? Because the correlation coefficient, I've at least started working in the notebook. But this new one, which is even more simpler, even more widely used, but I didn't start with it, but eventually I got to it, are the ideas that I'm going to share with you now. And these also fall under the statistical measurement category. So we are all aware of the arithmetic mean or average function, right? It's the mean function in Python, or in most languages, or pretty much all languages, I think. And it returns a single value. You give it a whole set of values, you give it an array of values or distribution, and it'll give you a single value. Again, the same arguments about single values, right? But let's see here, there's some more things here that we need to consider. We know specifically with mean that if a distribution or a set of values contains outliers, then those outliers can dampen the end result, which is dampen the single value that comes out of it. Now, just to keep this discussion simple, I'll say we all agree on a standard single definition for outliers, right? Because I see there are various methods of extracting outliers, and everybody will have their own opinion, and they could be right. But we don't want to diverge into that discussion. We want to keep this discussion more objective towards getting the end results of this limitation here. And so if we go further from there, so saying that if we agree that the outliers dampen the end results, but then if we say, but what if we accounted for these outliers in our end result, right? How do we do that? Well, we'll come to that. But also, what about, instead of getting a single value as the mean, which the mean function gives, we had hierarchical mean. Now, what do I mean by hierarchical mean? I mean hierarchical mean like a tree structure, a categorical. And I again will explain that idea further, and you'll see in the following slides what I mean by that, right? So that way I'm not just throwing words in the air, but you can see them in the coming slides. And none of these have been expounded yet. These are just very fresh off the oven into the slides, right? You are the first audience to see it. So we know the mean function works like this, right? You pass it in a list of values. So, the data type doesn't matter. Give it a set of values, it returns a single function. But we were talking earlier that if there are outliers in the list of values, like the previous set of values that I shared, it didn't look like it had outliers, right? But that's discussable. But in this slide, you can see on the top left corner, the first plot shows you all values, and you'll easily spot there's a wide gap between the values after 10 and 60, and then there are 3 such values which also have gaps between them, but then they're very large values, right? Now that it itself tells you that, oh, there might be outliers in this, right? So that means there is room for segregating these into categories, and I call these categories, and you can define these categories based on inliers and outliers. So what is the outlier? Anything here, now this is specific definition here, just for this example, the values that are less than 3 or greater than 50 are considered to be outliers. So you have 2 types of outliers, the lower outliers, which are less than 3, and you have high outliers, which are greater than 50. So that gives us 3 groups of values. So from that one set of distribution, which is called all values, we have now 3 groups, right? You have the inliers, you have the outliers, which are of lower and higher quality. And you can see now, once we do that, we see that the mean that is generated by each of them is very disparate and separate from each other, and there's a wide gap between them. But also it makes sense, right? The population is higher. Again, this is discussable, but from the distribution, it appears the population is higher between 3 and 50, whereas there's sparing values of 60, 80, 100, and then the sparing values of 1 and 2, and these are dampening the mean value, right? See, look at the overall mean value. It's 23.75, whereas if you take each of the groups, they are way off. One of them is 80, the other one is 1.5, the other one is 6.0. So obviously, these don't belong together, looks like. And again, that's discussable. It also depends on what you define your inliers and what you define your outliers, right? So this all is very dependent on that. But if within the context of this definition, this looks like it holds some grounds, right? Again, I'm happy to discuss this further. So that's the issue, and that helps with the categorization. So when I said earlier, what if we accounted for the outliers? And this is what I mean by what we accounted for outliers. We have a function that takes in the values, it takes in our limits for the outliers, or the inliers, and of course this is a very basic skeleton function. It can be improvised. At the moment, it doesn't take care of all the edge cases and corner cases that happens in the real world. In theory, this looks like it's a happy path, works in many cases, but maybe not works in many cases. So you pass in the limits, and I've shown here, but you pass in the inlier limits between 3 and 50, and then the function knows that, okay, I need to break it into 3 groups, because one group on the left, one group on the right, and one group in the middle, and I want to compute different means for each of them, because that's where, that's how I will know the population mean, and it also returns the mean of the whole distribution, which is 23.75, but it also gives you the lower limits, the lower outlier mean, the high outlier mean, and the inlier mean. Okay, this is what I meant by accounting for outliers, right? So this is one idea. So this is one of the ideas I was talking about, and this is one idea that we are thinking about. Now, the other idea is the hierarchical means I mentioned to you earlier, right? So if you look in the diagram here, you can see these are histograms, and I've used histogram binning. If you can see, the right on the top has the highest number of bins. I think it's about 100. And as we go further, it's 50, then it's 25, and then the last one is 5. And if you see, it's the same distribution. As you reduce the bins, it increases reduces the number of bins, but it increases the size of each of the bins, and it accommodates all the values in those bins. So actually, it looked like there's a lot of frequency, a lot of smaller bins that are getting fitted into bigger bins. So this actually is because it's grouping, merging, and gathering the values as we are going from a lower bin value to a higher bin value, which is kind of the idea behind the hierarchical mean that I have in mind. And I'll explain in the next couple of slides again what that actually is. Think of it like this. You have a distribution. It's a very simple case. It may not be applicable. It's a very simple case just for the presentation. You have these distribution values in the distribution. And at every stage, we compute a mean of the nearest values. In this case, we've just taken 2 values, but in a real practical world, it could be different sets of values. And then we keep doing that till we come to a single value, right? So the single value is the mean that you computed, and which would be the mean that your mean function may have returned. But at least here we have the steps and the history. Remember, there was one slide earlier we were talking about, hey, where are the steps? Can we trace back? Is the history lost? Is there no history? Is there lack of information? At least from here, we can trace back from the mean to how the mean came about. And obviously, depending on how we write this function and what parameters we give it and how we define closeness and how we define the clustering, the outcomes of the means at every stage would vary. And it could also mean the final outcome of the mean could also vary, right? So now this is the second idea, right? Now, how about putting the two ideas together? Remember, the first idea was about accounting for the outliers. And now the second idea is hierarchical mean, right? In the accounting for the outliers, we also had mean that was produced for each group. And now for each group, you have not a single mean, but a hierarchical mean, right? So if you put that together, can you envision hierarchical means applied to the three different groups, to the lower outliers, inliers, and higher outliers? So now we have more information about the mean value of that distribution, right? We know there are multiple categories, at least 3, and in each category, there's a hierarchical incremental stage or process in which the mean is calculated based on the closeness of the values. Again, all of these can be defined by the end user, but in a simple case, it could look like something like this, right? So this was the first and the second idea put together. And this is what I was thinking about, where the limitations that I did see are now actually getting addressed in a different way. Is it useful? Is it applicable? It's something to discuss. So I hope that the two ideas that I shared, I know they've been quite abstract, and you might be thinking of other corner cases, and you may be thinking of something else. And I hope I didn't confuse you, but I hope that these are clear enough. And I've also tried to create a notebook out of them and share with you so that it becomes even more clearer, because once you start seeing code and you see in practice, then you're able to put 2 and 2 together and able to put the picture together. So let's, because we're in the constructive thinking mode, I just have a few more questions to ask. And so let's ask these few questions and proceed further. That way, we are doing justice to the subject. So the first question is, and I don't need answers to these, but these are questions for us to think about as well, right? What is, and I'm not going to give answers to these either, because I don't know the answers either. We need to discuss this further and figure it out. So what is missing in these ideas or observations? And are the results or conclusions that I've drawn correct, right? So this is the first and foremost important question. You will ask that as well, but I'm going to ask you that question so that we can both ask and come to a conclusion. Now, if they are correct, now it's not necessarily all parts of it are correct. Maybe some parts of it are correct. Then why are those some parts that are correct, right? We need to find out that why. And the other question is, if there are parts that are not correct, if all of it is not correct, it's fine. We still need to find out why they're not correct, right? So that's something for us to also find out. So based on that, we will have positions, right? Sometimes some of us will think, no, those parts are correct. And sometimes some of us will think these parts are not correct. We need to be able to justify our positions. I am not saying I'm able to justify. I'm only going to give some examples and some arguments and keep building these notebooks and sharing, and then people can comment. And we need to all figure this out together, right? Can we justify any of these positions that we are taking based on the ideas and observations so far? Or do we need more examples, more discussions, more scrutiny? So I'm thinking by now, you must be already satisfied. And for those who are not, we can still continue with this discussion, that we have addressed the limitations aspect that we started talking about, that this whole discussion or this whole presentation was about. And if not, then I'm happy to take those on during the Q&A sessions. And hopefully some of you already have. I heard from Ion that some people who couldn't attend the session have thrown in some questions. We could also address them. Hopefully they're within the scope of this discussion, and hopefully they're also within the scope of my understanding, because I don't necessarily know answers to everything, but I will try to answer. And so let's summarize, because we're heading towards a Q&A session, but let's summarize. So I started off throwing this idea and also sharing with you how I came about with this idea of studying the limits of statistical measurements, and what led to what, and then finally it led to this notebook that I created. And of course, people have also given feedback, which I need to apply to the notebook. The notebook has examples and plots and arguments and commentaries on there, which we have shared. And it so happened that after doing that, there were more questions that came up, which I couldn't make it part of the notebook yet, but we've seen those questions as part of this presentation. And we've also seen some new ideas and insights that came about after doing all of this, right? Which again, aren't part of the notebook yet and only part of this presentation, but will be made part of this notebook soon. And finally, to continue with our critical thinking, we asked the last set of questions to question all the things that we've spoken of so far. So in the whole process, without even talking and pointing out this is a limitation, this is not good, we actually noticed the limitation and immediately tried to overcome it by doing some sort of an alternative solution. I think you'll agree with me on this, right? Because both the notebook and this presentation has that kind of an angle to our discussion. And we've tried to be curious as well. We've been asking questions. We don't have the answers to all the questions yet, but in the process, we've been curious and constructive as well in going about with this topic. So my humble request is also that please, when you go through this presentation, offline or online, and go to the notebooks and the slides, and if you have any feedback, please share them with me, and please share the constructive feedback or feedback in a constructive form, so I can use that and others can benefit from it as well. So in closing, I will say we cannot always win, and we'll see why I mean by that. So firstly, if let's say this forum agrees with many or all of the things we've just discussed in these slides in the notebook, we are still in the minority, right? Simply because others may have other valid points that we haven't considered because we haven't heard them. And also that our arguments may need more ground, simply because, again, we don't have the experience and we haven't spoken to everybody. And it, again, a redundant point here is that we could be wrong about many things, partially or fully, right? So we need to be aware of that. So hence those questions, hence not taking positions. There's also another side to it, right? The things that are correct or applicable may only be applicable in certain contexts, and the things that are less correct or wrong and or not applicable may be only not applicable or incorrect or less correct in those other contexts. Hence, context is important here, and so we need to also make that clear and understand that. So as you would all agree that no work or no learning or no presentation is possible without resources. And I've gathered a lot of resources along the way in my journey, and I want to share some of them with you. And so these are some of the resources. I would humbly request you to go through them, not just now, but after this presentation. I've learned from all of them, many of them actually. A couple of them are my own GitHub repositories where I gather these resources. But there's also another, like Virgilio, I contribute to some small parts of the content there. I mean, they have done great work in putting together the content there. And I've shared some of my Kaggle notebooks and other notebooks link as well, where you can also learn from and contribute to and share things with me so I can learn from your experiences and your feedback. And some of the people, there are many others to follow, but if you follow some of these to start with, they don't need to be mentioned. Many of them are very popular in this sphere. But I'd like to emphasize that the O'Reilly resources for machine learning, data science, math, statistics, probability, these are second to none. They bring some of the best speakers, the best thinkers, and they create some of the best contents out there. And a lot of that content is also free. So please visit their website. And I've shared some link as well. You can also use them and get further with your learning. I know we're coming close to Q&A, but I want to lastly quickly share this other book that I have a copy of as well, and I've came across this book quite some time, and I immediately bought it. Is this book called Numbers: The Universal Language? You can find it on Amazon. It's like a Reader's Digest book. It's very, and it's also like the Reader's Digest format. I think it's from the similar publication, if I'm not mistaken. Maybe I am, but it's printed in a similar form, and you can learn about the history of how counting and numbers and statistics came about from various cultures, and they go way back, not just 1,000 and 10,000 years. I mean, you'll see from the book what I'm talking about, and it's covering lots of different cultures worldwide. So it's a very universal book, just like the title sounds like. So that's something I recommend you do. Once again, I'd like to thank the Kaggle Days Meetup, the Delhi NCR branch, of course, and of course you for being here, spending the last 46 minutes, as the timer shows me here, listening to me, participating in this conversation. Obviously, now we'll be going to the Q&A session, and we can talk some more. But once again, thanks to the organizers and you, the audience. And with that, we can jump into Q&A. If there are some burning questions already somewhere, I think Ion has some questions for me. Okay.
So thanks, Mani, for the talk. It was really useful, and like a lot of the questions that the audience, like those who couldn't join, had sent me the questions. But now, after listening to the talk, I feel that a lot of the questions that they asked are getting cleared, because might be the things were not getting conveyed through the presentation. Might be now when we had this live session, maybe a lot of the things that they were asking gets covered. So we won't be picking those questions. Like though we have a lot more questions to cover, starting from the right basics to the little bit of advanced stages, we would go step by step. But clearing the live chat questions that we have. So
Sure.
Syed Fareen is asking, is this one is stratified sampling? So when you were giving some examples, right? So like Syed is asking, is this one is stratified sampling? So the like while you were showcasing the slide, do you prefer, like, do you want it to refer to this as stratified sampling or something like that?
So I'm not aware of the stratified sampling concept. I'm thinking it's some sort of generating random distribution from a bigger set. It shouldn't matter. What I have done is, if you look in the notebook, and I would recommend that he goes and looks into the notebook, you can see the code on how I have generated the distribution. Right? That would clearly answer to, because I'm using NumPy's normal function to generate a normal distribution, and I'm generating random numbers between 0 and 10, and I'm generating hundreds of them using the random function that Python gives you, right? So there isn't much of a sophisticated way of generating the distribution. And to be honest, if you replace them with any other function that generates distribution, the point was just to do the argument here that distribution correlation coefficient is the information is insufficient that's coming back from the correlation coefficient function, right? So you pick any distribution, even if it tells you a number which may be correct, it's still insufficient information, right? Because now going back to the slides, you can see we are missing so many things, right? What does 0.24 mean? When we have already seen from the graphs that at many times it's negatively correlated as well, but the end result is positively correlated. Okay, it's a fight between a positive correlated and negative correlated values, and because the positive correlated value is higher in number, it wins the fight, and the reduced value is 0.24, right? But what if they were very close to each other, right? What if one was 90 and the other one 70? They are not small numbers, right? 90 and 70. The difference is a small number, but that information is not there, right? And also, it's spread across, isn't it? It's not continuous. Like, is it continuous? Is it spread across? And there's, when I had those questions, they were there to find out all of those bits and pieces of information, and then we can create a better picture of how is this happening. So I think the answer is, I would suggest for Saeed, or if anybody else has asked that question, go and have a look at the notebook to see how I generated the distribution, and then use your own methods to replace those distribution functions and see what the end results are, and see if the notebook generates sensible values or not. In any case, there'll be the same questions, there'll be the same problems, there'll be the same limitations. This is my view. But if you find something different, I'm happy to take that on.
Got it.
I
So
hope
it's
that
like
I hope that satisfies and answers the question.
like at least if I was thinking from the scope of Syed, so definitely it gives a clarity that how should we approach, or what we need to do, or at least what should be the next steps in order to get more visibility on this question. So Sayed also answers. Okay, so thank you, Sayed, for your question. So the second question we have, it's from Leonardo.
Oh, I know
Uh,
Leo. Hey, Leo. Thanks for joining. He wasn't sure if he was going to be there. Okay, what's the question? Interesting one.
so it's like I have flashed the question on the screen.
Yeah.
So it's like
So it says, yeah, it's interesting way to do computer correlation between streaming data, time series problem, and get an enough window size to compute a correlation between two variables. I think his question goes further, right? With that in mind, how do you define a minimum window size to reach a nice correlation? That's excellent, because what's the definition of a nice correlation, right? Especially if you have a real-time data, you wouldn't know the next set of data that comes in, the next stream of data that comes in is going to disturb or is going to be the same as the other one, right? So you need to first define what is nice correlation for you, right? And then the minimum window is an experimental department, right? You have to play around with what size do you want to use. I would say that I have used minimum 4, because if you use anything less than 4, the correlation function returns nan, which means it needs a minimum set of values to compute the correlation coefficient. So start with 4, or whatever the minimum you find with your correlation function, and then keep increasing that and stop at a point where it smoothens out, where it starts not changing anymore, and then stop there. So you might have to have multiple graphs that take different window sizes, or maybe one graph which takes different window sizes and overlap those correlation, and see the moment it starts overlapping and doesn't deviate anymore, that's your maximum point, and the minimum point is 4. So anywhere between 4 and your maximum point. That's what I would suggest. See, here the nature of your streaming data will define what correlation coefficient is. One day you'll get a good one, and another day you won't get a good one. So you might have to play around with it. But once you do this minimum maximum game, then you know that between this value and this value, no matter what the streaming data is, we'll get a good correlation coefficient.
Got it. So it aligns to a question that we had from Rajan, who is not able to join us. So Rajan also
Mhm.
had a concern around this, like how should we do this, or what should be the minimum window size and kind of things. And I was also talking to him before, like as he sent the like question, I reached out to him that, hey, what's the thing, and like it was really an interesting question. So that's the discussion there went, that if we are doing machine learning, if we are doing AI, if we are doing data science kind of things, it's all about experimentations. You cannot be sure that, okay, this is the minimum thing or this is the maximum thing. It's like maybe certain things work for me, there are good chances that those won't work for you in your environment or in your
Exactly.
scenario.
Exactly.
So
Context,
that
right?
definitely
Context.
helps.
Context is the key here, and that's why when I said you can not always win, right?
Hmm.
So whatever I said here, somebody else would say, in my lab, none of this works. This presentation doesn't work for me, because in our lab
Yes.
we have a whole different setup. We have taken care of all of these problems you're talking about, and the solutions you're giving us are not the solutions we are using, and it works for us, right? It can be the case, right? I'm not like Professor whatever, whoever's the king of machine learning algorithms, or maths and machine learning expert. I'm not any of those people, right, to suggest use this, and hence a lot of these are experimental. But yeah, please play around with it. Like, I mean, the two ideas that I shared about the hierarchical means and segregating the distribution into different groups, I hope that they are going to be useful, because they need to be refined further, but they'll definitely uh, have some place in people's systems or libraries, and a lot of the libraries may need to be rewritten for those
Got
functions,
it.
right? Because
Yes.
just now mean is just returning one value, but if you have our mean function, the better mean, you get all the values, but then you have to manufacture those values and
Yes. So
define
that,
the
that
function.
that's how this data science industry, I would say, moves on. Like a lot of updates, or like the changes, like we try to accommodate the changes which really works better for the society as a community. We definitely try to work around that. So we had one question from Kinjal, like he I don't know, like the person shared a question that they were asking that, okay, whenever I try to go to certain interviews, like I'm not that much heavy on statistics and statistical measurements. Try to like statistical measurements are not my very strong points. And in the past, I have seen certain interviews where I have performed badly, or I have not performed that much greatly at when the interview started asking me around statistical measurements and the limitations and the things like that. So he also tells that okay, this session should have been 3 months back when I was giving my interview.
Time
So.
machine. Time machine.
So yes, what would be your suggestion to like let's say to tackle these kind of things in an interview setup? Because we now know the content, and you have been very great at explaining the things and sharing the things. But like let's say we when we try to translate this into an interview environment, I know that's a tricky question because the interview setup might change as per the situation or as per the company. But how?
Mhm.
What would be your suggestion around tackling these statistical questions or statistical measurement
So,
questions?
so I'll try to give an answer that can be used everywhere, right? So this is how I do it. Like, for example, I prepare myself for everything and nothing.
Mhm.
So I don't prepare myself only for the interview or only to talk in a presentation or only to talk to a friend, right? You need to know your subject. And I don't want to put pressure on anybody by saying things like, um, but when you start studying a subject, you want to go uh, deeper into it and ask questions and mainly know, what you don't know, and how things come about. You see, the reason we don't know these answers is because we have not inquired about them. We know those answers, but we have not mapped those questions with those answers in our head, right? So we know the answers, we don't know the questions. Hence, we are not, because we haven't mapped the questions to the answers. Is that's because we don't know it. That's when we say we don't know it. But if someone tells you, oh, actually, this is what I meant. Oh, yeah, okay, that's what you meant. Oh, sorry, I already knew that. But that's kind of doesn't work, right? In an interview, if you say that for everything, then they'll say, you're faking it, right? But the way to work is that go from your results back to the source for anything like if somebody says this model is perfect, right? So what are the two angles to it? It's perfect or it's not perfect, right? When it is perfect, why is it perfect? When it is not perfect, why is it not perfect? Is there a state in between? If that state exists, then inquire about that state. This is what we did with our slide earlier, right? Positively correlated, fine. When is it positively correlated? For how long? And we can add 10 more questions, depending on who is talking on the topic. I'm not an expert in that field at all, so my questions are limited to 3, but the experts could add 7 more questions. But that's what I'm saying. Inquiry, inquiry, inquiry. When you start inquiring about everything you already know some of the things the other things you don't know, somebody else knows. Somebody else doesn't know, the internet knows, the Google knows a lot of stuff. But you have to start with inquiring, right? So that way you don't prepare for the interview, you prepare for life, you prepare for everything. Like, I'm not an expert in any of these things, but if someone in the expert field comes in, I will know how to adapt myself to ask the right questions, get into a discussion, and not make a fool of myself, right? But also, if I don't know something, I'll tell them, I don't know this, I want to know this. How do you do this? Teach me, show me, right? So that is the angle you want to. Once you switch to that gear, then you don't need to worry about how do I prepare for interview, how do I prepare for the presentation, how do I prepare for the job, because now in the job I have to do the real thing. Whatever I said on the presentation and the interview was theory. But so the way to prepare is inquire. Keep going from what you know to how it came about, which is what I have been doing with machine learning, right? People say, oh, yeah, correlation coefficient tells me this is the same as. But then I went further. How is it computing that? Okay, what does it mean by that? Okay, let me look at the distribution. Let me map it. Let me plot it, right? The moment I started plotting, okay, positively correlated means if this rises, that rises, right? But sometimes this rises a lot and this rises only little. Or sometimes this rises a lot and this rises a little. That's also correlation coefficient. But sometimes both of them rise at the same time. That's positively correlated, right? What's negatively correlated? Exactly opposite, right? So there are 6 states, right? Now you have forgotten there's a no correlation state as well, right? When it is not correlated. And I was trying to find an example to come up with that no correlation. To be honest, the best one I had is 0.03. I couldn't get a 0, right? So that means I have to really add a lot of noise to my distributions and make them really wide apart from each other. But I'll never get a 0. I'll probably get a 0.00. I'll get a very small number. So what did I do? I started inquiring, because on the internet, all you have is definition for no correlation. You don't have an example of an exact distribution that is not correlated. They have shown graphs and everything, but how did they come up with that graph? So now when you start drawing them, then you see the limitation, right? Then I started playing, like, if I won't show you the notebook, but there are some notebooks where you send in sensible distributions and the correlation coefficient is returning nan, right? So I had a distribution of zeros and I had another one with ones, right? They are not correlated at all. So it should return zero. It shouldn't say none, nan, right? Because one is becoming zero, the other one's becoming one. One is becoming, and it's going on forever, the whole distribution. Logically, if you look at it with the eyeball and if you plot it, they have nothing to do with each other. Why is it saying nan? Nan is not the same as zero. For nan, I cannot say if it's nan, say zero, right? Because it says nan for many other instances as well, where it's not the same type of distribution that I've given. So if I start testing that function, I will already go to the hilt with it. So this is what you want to do with your learning. So to answer to, who was that gentleman who asked the question?
Kinjal. So it's like,
Kinjal.
yeah.
So gentleman or lady, because Kinjal can also be someone.
Yeah.
Okay, so let's be politically correct. He or she should inquire everything that they know. How do they know it? How do they know it's correct? What's there to collaborate with it? Because that will lead them to those statistical instances where they have these statistical, like, I have no statistical background, right? How did I even coming with this presentation? It needs a, what, did I do some course? No, I didn't, because I kept inquiring. I kept looking. Like when you're on Kaggle, you get a lot of things thrown at you saying, oh, this is like this. You don't take it at face value, right? You go and inquire. So I started playing with the submission data sets, because then I wanted to see, okay, this is my base model. This is my new model. How well are they correlated? Because closer they correlated means the model is doing as good as the base. If they're further away, they're not doing as the base, but then maybe it's doing better. So that's where I started inquiring into correlation coefficient. Then I started thinking about averages, because averages, we know, mean, we know there are problems, because outliers dampen mean. So then I started, but there should be a solution to this problem, right? So when you hear about these things, you should also think about, is it a problem? Can I solve it? And make a note of it if you can't do it now. Just inquiry, and experiment with the distribution. Don't take it by face value. Plot it, graph it, play around with different things. You might look crazy. Like if I show you one notebook, it looks crazy. But I know when I refine it and share it with people, then I can share some of the learnings and I can show some of the shortcomings of the correlation coefficient function, because it cannot handle a lot of the distributions I've been giving him, right? So you know these when you talk, and when you then present yourself like that to the interview or anybody, they know you know the topic, because you've already played with things that they don't know about, right? Because how many people
Yes.
know that correlation coefficient returns nan? You know, because you played around with it, and you can tell them, like, okay, open up your Jupyter notebook, create this distribution, now pass in correlation. Why is it happening? Can you explain? Now the interviewer is getting questions, right? Instead of you getting
Got it.
questions. So this is how,
Yes.
long-winded answer, but you need to know all of these things to be prepared for life, right? Not just prepare yourself for interviews.
So it's like that question opened up the ocean for the answers to other questions that has been covered very well. So it's like the first thing that is like, be curious, and if you are in data domain, I would say be curious and be not do not fear to be on an experiment mode, I would say. So
Exactly.
thanks, Mani, for those tips, and I hope those answers the most of the questions that are there. Like, and you have Mani on LinkedIn, Twitter. Do reach out to him for any further guidance or any other concerns you have after going through the PPT or after going through the notebooks. If you have any concerns, reach out to him. He's an awesome guy, and he would definitely help you with your concerns. Thank you all for joining, and thank you, Mani, for giving us such a beautiful session on this limitations of statistical measurements. Because when I flashed this topic to the community members, a few of them get to me that, okay, would it be very much theoretical? How would the things go? Would this be a mathematics book, or how would the things go? So it's like on that line, it definitely went very good, and it's like very intuitive session, and it would be useful for those also who couldn't join us live. So thank you for that, and thanks for making the presentation so
Thank you.
so well structured. Thank you,
You're
Mani,
welcome.
and
Yeah.
thanks to all for joining us today. Stay safe. Bye bye.
Cool. Thank